Okay, so I'm going to do something slightly ambitious. In 5 minutes, I want to tell you a mathematical theorem and make sure that all of you understand it precisely. I think it's accessible, at like middle school level, so it should be okay. But I mean, you will see, but it's very, very elementary. But the reason I'm doing this is I would like to ground the discussion in what is really the level of intelligence of those models right now. And Terry and Damek talked about some examples this morning, and what I'm going to do is just do basically the same thing, but trying to deep dive a little bit more into this example, explain what it is and how it compares to human intelligence. Okay, so this is a combinatorics question. So you have a graph, so a network with vertices and edges, and the most basic thing, like one of the most basic questions that you can ask is you can count subgraph in this graph. So maybe I count the number of clicks, the number of fully connected component, or the number of anti-click, empty independent set, or I count the number of subgraphs that looks like an H. I have some collection of things that I care about and that I want to count. And I'm asking myself, are there constraints between those different objects? Like if I count, I have that many cleats, what does it tell me about the number of H's? Okay, so this is extremely basic in combinatorics. Turns out that it is incredibly hard. In fact, it's completely impossible. So in general, if I ask you a linear inequality between different subgraphs, I ask you, is this true or not? This is in general undecidable. Okay, so there is no way to answer this type of question, which is kind of crazy. But the most basic version, which goes back to 1904 by Mentel, which is the first result in extremal combinatorics, is about specifically the relation between the number of edges and the number of triangles. Okay, if I tell you how many edges are in a graph, what does it tell me about the number of triangles? And Mentel's theorem in this picture that I will explain in a minute is exactly just this point. So let me explain this picture. On the x-axis, you have the edge density. Okay, so the number of edges that are present among all of those that can be present. And on the y-axis, I have the triangle density. So among all possible triangles that can be present, what is the proportion that I actually have? And it turns out that there are constraints between those things. In particular, if I have enough edges, then I will have a triangle that appear. Okay, so this is Mentel's theorem, tells us that once we cross that fraction, then we need to have triangles. Okay, and it's a very difficult, mathematical result to show that this is a lower bound, so there is nothing. You cannot have graphs which have this edge density and that triangle density. Very good. Now you will note that this shape is non-convex. Okay, we don't like non-convex things. It turns out that if you ask the same question for trees, then what I showed with Nati Lineal more than a decade ago is that for trees, these sets of possible relationship between subtrees is actually a convex set. And then the question became, okay, what is the tree equivalent of this edge and triangle density business? A triangle is not a tree, right? A tree is something that doesn't have cycles. So we ask, okay, what is the equivalent of this picture? So you can think about it like, on two vertices, I have only one tree, which is an edge. On three, I have also one tree, which is just, a path. On four vertices, if I add one more vertex, then either I connect it into the middle or I connect it at the end of the path. So on four vertices, I have two trees, either a path or a star. So in terms of proportion, it's not interesting, because if I have a certain proportion of paths, then I have 1 minus that of the proportion of the other one. So the first interesting case is this one on the left, which is 5 vertices. Okay, so on 5 vertices, there are 3 isomorphism type of trees, which is either a star, a path, or the thing that looks like a Y. And now I can start to do something interesting, which is if I tell you that I have a certain proportion of stars, what is the possibility for the proportion of paths and the proportion of Ys? Okay? And it's really a two-dimensional picture, because since I have 3 things, the sum of them is always 1 for the total proportion. So I can start to draw pictures again. I can look at proportion of paths versus proportion of stars, and what we conjectured in a 2013 paper. In the 2013 paper is that this is the set of possibilities. And the shape of the convex set was determined by these things that we call millipedes. So you see, these are like, it's a long path, and then I have this thing of degree d. If d gets very large, then I have a lot of stars and very few paths, so I get up there in the corner. Okay, details don't matter. What we were able to do, and now we're going to get to the AI part in a minute, we were able in 2013 to prove this is a lower bound. So the convex set has to be above this red line, and we're not able to show any of those faces of the polytope to be tight. I have given this problem to many students when I was at Princeton. Every year, a new crop of students would come. I would tell them this problem. Nobody would come with a solution. I myself spent, a month working on it. Natalie Lineal spent some time. We couldn't make progress. Then finally came three very good students: Ora Mania, Catherine Edwards, and Catherine Sutko. They were good students before too, but these three. And they, together, we were able to prove that this first part of the polytope is actually tight. Now, it corresponds to something extremely simple. In plain language, it corresponds to this inequality that for any tree whatsoever, if I count the number of y's, it's always going to be less than 9 times the number of stars plus the number of paths plus 6. Okay, very good. Then, in the same paper, we were able to disprove everything else. So nothing else that we conjecture was true. Everything is false. And you can look at these trees at the top. They kind of disprove everything. But kind of very weirdly, this second inequality remained open. So this one could still be tight. And it corresponds to this inequality. Okay, 29 times y is less than 42 times s plus 144p plus a constant. Okay, and this has remained open for 10 years. And with GPT-5 that started to be good at mathematics, I thought it's a good time to revisit this question. If you ask this question to GPT-5, no luck. There is no way in hell that it's going to be able to solve this question. This is way too hard. So what we did is, and this was alluded to this morning, we built scaffolding around GPT-5. In this case, it's a general scaffolding. It doesn't have to do specifically with this problem. Although this is a very interesting question also to build scaffolding specifically for certain problems. If you already have a proof technique in mind, an approach, then you could build a scaffolding to kind of execute on your approach. But here it's a general scaffold where there is going to be some agents that propose ideas, some agents that execute them, some agents that verify them, some agents that merge different things, etc. I'm not telling you exactly how much compute we spent on this, because you can do things in parallel. But at the end of a sequential time of computation of 2 days, it came back with a proof. But importantly, I did not ask the second inequality straight up. This is also something very important to understand. I knew if you just ask the second one, it's going to be way too hard. So what I did is I asked the first question first, for which I already knew a solution. The model thought for 2 days, came back with a solution, and I put that one in context, and then I said, okay, now go attack this, generalization of it. And it came back with a proof. I'm up with my 5 minutes. If I had more time, I could show you the beginning of the proof, because what's interesting is that in this proof, it comes up with kind of a miraculous identity on trees that I have no idea where it's coming from. And I have asked, experts to spend a lot more time thinking about combinatorics of trees than me. And they also don't know where it's coming from. And it really kind of solves this problem. And this, in the discussion of how can academia interact with, frontier labs and all of those things, here is one example of a kind of a question a little bit out of the box that academia could consider is, with this scaffolding, I have millions of tokens. I have, dozens of book worth of material that the model has written to arrive at the final solution. Where in this, library of knowledge that the model has written is the moment where the model got the insight, So I give you these 10 books. Tell me, find an automatic way to discover the insight. This is something, I think it's important. One thing that I like about academic freedom and academia is that you're able to ask questions that were never asked before, that just come, naturally out of the progress of technology. So we shouldn't always try, to reuse questions from before. Anyway, this was just a general comment. I'm going to stop here. Thank you.